2003, what number?
Problem 31.
31. Oh yeah, this is a fun one. Okay. This one right here, what part?
A.
Just part A?
I think so.
Okay. So part A, this is page 122 on my practice final action. Spring 2003. Will lead azide precipitate? So anybody, what do we need to figure that? What's our solving technique? Just Q, because it's will it precipitate. So I need the initial concentrations. However, I now notice two things are being mixed. Notice the two things are mixed, so I need to do a dilution problem before I can do part A. Is that okay?
All right.
So let me set that up for you. Okay, I might need that in a second, so don't steal it yet. They're really excited about helping me correct things, and they're just passionate people up here. That's so awesome. Okay, so I've got the lead 2 plus. And the initial concentration is 4.0 times 10 to the minus 3. I have an initial volume of 750, and then my final volume is 250 plus 750, or 1,000. Is that okay?
All right.
And then I'll do the same thing for the azide. N3, no, the N3 minus. Its initial concentration was 8.0 times 10 to the minus 3 times 250 initially, and divided by its total, which is 1,000. Is that okay?
All right.
Once you have those two numbers, just use Q. Q is, this is for, see the compound is PbN32. So I need the initial concentration of the lead times the initial concentration of the N3 minus the azide. And then which one do I square? First or second?
Second.
Is that okay? So just plug those numbers down there. Are you good?
Wait, how'd you know whether or not to square the second or the first one?
Well, if you write the reaction, how do I know what to square? Lead 2 plus N3 minus, and to balance it, I need a 2 there. Because of that 2, it's squared, but you could have noticed there was a 2 here, and it had to be. This 2 goes with that 2 right there. So, if you didn't see it, write the reaction.
Okay.
Okay? Ready for the next person?
Yeah.
Okay, yes.
Could you just do part B of the same problem?
Oh, okay. I was about to give it back to you, but now they asked me part B. I don't know how long they're going to go here. Okay. Part B, find the equilibrium expression. You don't need to solve it, just set it up basically. And then I was super nice and wrote the acid-base equation out for you. Okay? So that's kind of like, the note is kind of like a hint. All right, so let's do this. Notice I have this, which is a KSP, and I'm going to add acid. So this is that mixed K question. There are 2 Ks, which you see I do have. I'm going to have 2 reactions, which I'll add, and then I'll do an ice table, but I don't need to solve it apparently. Okay. So let's write first the KSP. So you want to write both reactions. This is called a solubility expression. And then I'm going to add an acid. The acid will react with what? Cation or anion?
Anion?
Anion. How did you know that? That's right.
It goes with the negative.
Acid has a positive charge. It will react with something that has a negative charge. Or the anion is the negative one. So the N3 minus is going to react with acid. I'll just write generic acid here. The N3 minus will add a proton. The H3O plus will lose a proton. So I have a KSP here on the top. I always will have a KSP first. And then the second one, either you recognize it or you read the note where this is the reverse of Ka. You see that? It's the reverse reaction of Ka. So this is 1 over Ka. add these together, see what will cancel. Oh, hold up. What do I need to do to the second reaction?
Balance it.
Yeah. Notice the M3 needs to cancel, but it can't unless there's two of them. So I need to multiply 3 by 2 everywhere. Yes. Why do I want the M3 to cancel? Whatever is reacting to what I add, so in this case, the M3 is reacting with the acid, that entity has to cancel. It's basically being reacted all away with the acid. So we need to demonstrate that by canceling it. Okay. So let's rewrite the reaction. Okay, I think I got it all right. Now we go straight to the ice table. We ignore, the first one was a solid. We also ignore water, so 2 of them are gone immediately. Let's look back at the question for a moment. Okay, I think you can see the question, yeah. I know one of these three compounds, I know one of their numbers that is non-zero. Anybody know which one? H3O plus, lead, or the azide? Lead. I know one of them. Which one do I know from the question? I don't know lead. I don't know the azide, so I guess it's the acid. Okay, cool. How do I know? Okay, I'll just tell you. Yeah, because you know the acid, what is in part B telling me that? The pH. Remember, pH is negative log of H3O plus concentration, or this is 10 to the minus pH, which is 10 to the minus 2. That's the one I know. The other 2 are zeros. So I'm going to minus 2x, because the 2 right there, plus x plus 2x. Or 10 to the minus 2 minus 2x, x, and 2x. So KSP, oh no, K total equals x times 2x squared, all divided by 10 to the minus 2 minus 2x squared, yeah. And that equals KSP divided by KA squared. Because when I add the reactions, I multiply the Ks. And obviously, you can't solve this in the final, it's really crazy. So that's why I said just set up the expression. But this is a fairly typical kind of what I would call mixed K question. Next. Yes?
This is from here.
And I'll come down here next, unless it's on this. Okay, really quick on this, and then I'll go to a new question. When you write a reaction, how do you know to write H2O, or in this case H3O plus? If there's nothing else, you add water. In this case, I knew to add this because it was just right here. I carried it down. But if you're wondering why did I know to write that there, that's because instead I have a pH of 2, or I know I'm adding acid if it's less than 7. So a way to tell you what to add, in one way, and this is indirect, if I give you a number less than 7, I'm telling you add H3O plus. If I gave you a number, for example, above 7, I'd be saying add OH minus. If for some reason I wrote pH equals 7, you'd add water. Or if it said there's nothing else, if there's nothing else here, then I add water. Okay, new question. Yes?
So this is from your review worksheet. Number...
I didn't bring that, so I'll have to borrow yours.
Okay, yeah.
Okay. Hi, what's up? This was spring 2003, what number?
31.
31?
Yeah.
It was asking for that equilibrium expression that you just stop right there. So what I have written in brown at the very bottom. Yeah. Consider the following. This I think I got this actually off of a final somewhere. So This is actually a final exam question. I don't know where. I forgot where I found it. Okay, I want to know the boiling point of water on the surface of Mars. And I give you all this random data. You may or may not need all this data to find the boiling point of water. Let's look at what else we have. Okay, well let me ask you this. Do you remember what boiling point, if you have a lot of other data, would be associated with what equation? The Clausius-Clapeyron, that's right. Boiling point tells you that the boiling point is at what pressure? 1 atm or more generally. 1 atm is our planet. So it might be different on Mars. We'll have to read through. Okay, so the boiling point of water on Mars, does it give you, here's the Earth, Mars surface pressure. We need this number right here. That's where water boils at that pressure. Okay? So, let me write that down. On Mars, the boiling point of water, the pressure is 0.015 atm. What's the temperature? What's the boiling point of water? 100, you better double check because sometimes it's different on different planets. Oh, boiling point of water on the surface of Mars, that's what we want to know. So don't assume it's 100. It's not necessary. Okay. Now, I need to do the Clausius-Clapeyron. What delta H do I need to know? Vaporization, that number's given. It's 44 kilojoules per mole. Okay, and then I need another pressure and temperature. Let's say this is temperature and pressure 2. What other pressure and temperature could I use? Looking at this data. In fact, you don't even need this data, but what else could I use? Yeah, I could use the Earth information. That's okay. So I could use 1 atm and 100 degrees C. Who asked it? Oh, you're up there. Do you want me to write out the Clausius-Clapeyron and then you can solve it, or just you got it now? Okay, you part B, right? Okay. Part B. So Clausius-Clapeyron, etc. All right, part B. How much heat is required to completely vaporize 1 liter of Martian surface water? And temperature is -50. Okay, what was the answer to part A? Did I give that in here? (288 Kelvin). That's the answer? Okay, cool. So that is about how many degrees C? About 15. Is that right? Okay. I just subtracted 272. Fair? Okay. No, I lost it. Okay. This is slightly different than the other one. It involves a boiling point. However, notice what I have. Well, first of all, I have a K. That makes me think maybe this is a colligative property question. And then I want the boiling point. That's associated with a colligative property question. And then I have some masses. I think that's what I want. I ultimately want the mass of hexachlorophene to the 120 grams of the chloroform. So let's try that out, see what happens here. Oh, here we go. Let's try this. Okay, do you just want to set up? Is that all you need, or was there something specific on here? Okay, what I'm doing is okay. All right, let's see if that works out. Delta T equals IKM. Delta T, well, first of all, K is given 3.63 degrees C per molality. I, these are all kind of organic compounds, so I for everything is 1. All right, what else do I need? Delta T, the boiling point of pure chloroform is 61.70. Oh, hi. Oh, okay, cool. Thought somebody was attacking me, but we're all good. You two are back. All right, yeah. I don't do that, you might as well do your thing. Let's see. And it'll give us a solution boiling point of 63.5. Okay, so there's delta T. Is that all right? Okay. So I'm going to solve for molality here. Molality is in units of moles per kilogram. Good? And this is moles of, what is the solute again? That one that starts with an H. And then the solvent is the chloroform. So I know not the kilograms, but I know there's 120 grams of the chloroform. So I change that to kilograms. I'm going to solve for mole and then convert to mass. Is that all right? You can? Okay. So you want Kp, right?
Right, yeah.
But it would be super nice if they would have given you pressures here.
Yeah.
Is that because then you would just do that. When that doesn't happen, what I would do is first see what unit is most common. Moles,
yeah.
Super common. That goes with a Kc. So what I would do is solve for Kc, and then the Kc equals Kp RT delta N. Does that sound familiar? I can write it down in a second.
Yeah, can you assume that it's like 1 liter? Like, because like when you're solving for Kc, you're using concentration, right? So,
oh yeah, can you assume it's 1 liter?
Yeah.
Let's see. Yeah, I would.
Okay.
That sounds good to me.
I was like, okay, that makes sense. Thank you.
Okay. Let's see. We want the density of palladium. Let's see what we have. We have the radius of palladium, and we know that palladium is a face-centered cubic. Okay? So, density is mass over volume. The mass is going to equal face-centered cubic. Anybody? How many atoms per unit cell?
4.
4. Way to go. 4, and then you just have to convert. So 6.022 atoms times 10 to the 23 atoms per mole. Yeah, I think I got that right. And then there's palladium. What's the molar mass of palladium? 106.42. 106.42 grams per mole. This is really the mass per unit cell. Then you're going to go the volume. The volume, I think we give you a list of the different lengths. Let's do the length cubed. I think it's R root 8 cubed equals R. Let's find R again. It's 137 picometers. So that's times 10 to the minus, for meters. How many meters? To the minus 12 meters. Oh, what do they want this? Oh, they don't tell you the units of the answer, but this would be meters. Typically, they'd want it in.
I know in some cases we want to convert from milliliters to centimeters cubed.
Yeah, so let's go to centimeters. I totally agree with you. That would be typical, but it doesn't state the units here. 100 centimeters. That'd be a pretty classic volume unit. Times the square root of 8 cubed. Is that okay?
Yeah.
You're going to divide those two numbers. You're okay with that? All right. Yes?
It was actually for the same problem.
Oh, what part?
It was just the density, because when we've done it before, we've done density in grams over some cube.
Yeah, which is what this is.
Yeah, but the answer they gave was grams over milliliters, so it's really not.
Oh, cool. That's a great question. What's the difference between a milliliter and a centimeter cubed?
They're both the same.
They are the same. So no worries. Yeah, 1 centimeter cubed equals 1 milliliter.
1 meter cubed is 1 milliliter.
Maybe, yeah. I would just convert it out. Is that okay? Yeah. I just remember that 1 centimeter cubed is a milliliter, and then convert from there if I need to. Okay, you want the vapor pressure of mercury, right? So, you need to think, as far as our class is concerned, in terms of reactions. Every time we're always working reactions, so it's much better if you write something like this. Okay? All right. So then you're like, oh, I need the vapor pressure of mercury. Let's write the K value for that. K expression. Kp specifically. That's the partial pressure of mercury. That's it. Because you ignore liquids. Remember? So once you have K, you have the partial pressure of mercury, which is the vapor pressure. All right, so how do you find K? You can either look it up. If you can't find it, then, which is quite possible, you can find the delta G of formation. So you find the delta G of formation of the vapor, and then what would be the delta G of formation for the liquid? Anybody? That's a number you should memorize. Delta G of formation for liquid mercury. You got it, 0. How do you know that? I had told you earlier. Does anybody know why it would be 0? Elemental form. Yeah, this one's not 0, so you need to find that number, the delta G of formation. And that's in the back of the book. On the test, we'd have to give it to you. And you'd go, well, this is products, delta G of formation of the mercury gas, minus reactants would be 0. And this is minus RT ln K, P specifically. Is that okay? Got K, and K is the partial pressure. Okay, cool. You can read that. Oh, yes, you can. So, we have this in that. Those are two unrelated compounds, so this is a mixed K question. 2 Ks are involved. One is a KSP, which is right there. Okay. And one, calculate KSP. So, and the other would be a KF, which is not listed here unless it's somewhere else in the problem. Or it's like here. Oh, whoa, okay. Now I don't even know how to solve it. Okay, oh. Nope. There it is. Okay, cool. All right, give me a confusing device here. All right, so let's try this. Oh gosh, where did that just go? I missed the numbers. Okay. AgCN dissolves, and then Ag is going to react with the NH3. We'd have to give you the KF on the test, and we would list the molecule for you on the test. So you would know it's this. So we need 2 of those. Okay, so you would add these up. You'd get AgCN. Oh, still need that thing. Plus 2NH3 goes to, let's see what's left. Ag and H3 2 plus Cn minus. Okay? I-stable. You ignore solids. This is this is 2 molar. It's 0.2 molar. That's given in the question. This is 0 and 0 minus 2x plus x plus x. 0.2 minus 2x, x and x. So K total, which is KSP times KF. Remember, you want KSP. KF is in the book, or we'd give it to you. That equals x squared over 0.2 minus 2x. Now here's the good news. In the problem, when it said...
Minus 2x squared.
Oh, you want to square? Yeah, oh, this would be squared. Okay, in the problem, this number is x. So you're going to put that in for X, and KSP will be your only unknown. Is that okay? Cool. Material, whatever that is, it is placed in a container. That container has 70 grams of water. This is at 102 degrees C, and it's 20 grams. This is initially at 25 degrees C, the water. The temperature of the system went to finally 30.25. We want to know the specific heat of the new material. Typical way, typical kind of question. Okay, here's the sum of the Q equals 0. There's a Q for the new material. I'll call it M for material. There's a Q for the water. It looks like there's no phase change. There's no reaction. There's no solution, so I think that's it. So 0 equals Qm, which is mCp delta T for M, the new material, and then water, mCp delta T for I'll put W for water. So let's see what we know. The mass of the water is given, the mass of the substance is given. We want to know Cp. The Cp of water is on the back of the exam. Delta T for the new material is going to be 30.25, that's T final minus 102. And for the water, it's going to be 30.25, same final temperature, initial temperature is 25. Can you solve it from there?
Yeah.
Okay, cool. All right, let's call it quits. Excellent, good luck on final.